This video 16 is titled Reduction of a Reducible Representation, Reduction Formula. We have seen earlier that if a reducible representation is similarly block factored, it can be reduced or split into the irreducible components by visually picking up matrices from corresponding blocks and connecting it to the basis function or functions. To recollect your memory, let me write again the reducible representation of C2V group on the basis of the coordinates of a general point x, y, z. Identity C2 sigma v x z sigma v dash y z x, y, z. The matrices are 1 0 0 0 1 0 0 0 1, a unit matrix of order 3. It is z, so it is minus 1 0 0 0 minus 1 0 0 0 1. X and z will not change. Y will change to minus 1, and here y and z will not change. All these are similarly block factored. The non-zero elements are along diagonal blocks. So we can pick out the numbers from corresponding blocks, like first row, first column, 1, minus 1, 1, minus 1. Second row, second column, 1, minus 1, minus 1, 1. Third row, third column, 1, 1, 1, 1. Since the first set of matrices or one-dimensional matrices being characters themselves corresponds to x, second one corresponds to y, third one corresponds to z. Since we know the Mulliken symbols of these irreducible representations, this corresponds to B1, this corresponds to B2, and this corresponds to A1. We say that the reducible representation denoted by gamma is broken into three components: B1 plus B2 plus A1. Such visual factorization is possible if the reducible representation is similarly block factored. But very often a reducible representation written need not be always block factored. For example, consider a general reducible representation E, script E, script A, script B, script C, etc., which are not block factored. It is possible to take similarity transformation of each of these with the same matrix, say L, in order to get new representation epsilon dash, A dash, B dash, C dash, etc., where epsilon dash is epsilon, L, L minus 1, A dash is A, L, L minus 1, B dash is B, L, L minus 1, C dash is C, L, L minus 1. By doing this similarity transformation on each matrix, you can get a new set of matrices which are epsilon dash, A dash, B dash, C dash, etc., which are now block factored. And now we can split it into the irreducible components by visual picking out blocks from corresponding blocks and linking into the respective basis functions. But very often it is very difficult to design or get a proper matrix L to do this similarity transformation. The procedure is actually known as block diagonalization. In this context, our great theorem, great orthogonality theorem, GOT, offers a simple formula to factorize an otherwise non-block factored reducible representation to the irreducible components. This reduction formula, which is a direct consequence of GOT, is mathematically written as follows. Ni is equal to 1 by h sigma chi I r gamma r n r. What do these notations mean? Ni means number of times ith irreducible representation occurs in the reducible representation. Chi IR is the character under class R in the ith irreducible representation, and gamma R is the character under class R in the reducible representation, and NR is the number of operations in the class R. Here the summation is done over R, which is representing the classes. This is the mathematical form. It is easily understood by one or two illustrations. In this formula, the simplifying aspect is that one need use only the character of the reducible representation. There is a shortcut method to write the character of a reducible representation. I am rubbing this formula off. We shall write it again when occasion demands. What is the simple formula to write character of a reducible representation under a set of basis functions? The formula is just like this. If a basis function gets completely unshifted, it remains where it is supposed to remain under the operation. If the basis function gets unshifted, it contributes the amount of 1 to the character. If the basis function remains at its original position during the operation, but changes as if it is multiplied by -1, its contribution is -1. And if the basis function gets bodily shifted to some new position, its contribution to the character is 0. Unshifted means 1. Unshifted but changes as if multiplied by -1, it contributes -1. Completely shifted, the contribution is 0. Now we shall illustrate this simple rule of getting the characters of a reducible representation by planning to write the character of reducible representation of ammonia molecule on the basis of the valence s orbitals on each atom. Let this be S1, let this be S2, and let this be S3, and let this be Sn, s orbital, 2s orbital of nitrogen. So on the basis of S1, S2, S3, Sn, in C3V group we have 3 classes: identity, 2C3, 3 sigma V. The character under identity, none of these orbitals get shifted during identity operation. So 1 plus 1 plus 1 plus 1, the character is 4. When a C3 operation is done, the s orbitals get shifted from its original place, but the s orbital of nitrogen remains there, simply gets spinning about its central location. So its contribution is 1, others' contribution is 0. When a sigma V, suppose this is sigma V, this is sigma V dash, and this is sigma V2 dash. All the sigma V's are conjugate to one another, so we need worry about only one of the sigma V's. Every sigma V contains 2 atoms, so 2 s orbitals. The sigma V, for example, has Sn and S3 already lying in it. Only these 2 get shifted. So 1 plus 1 plus 0 plus 0, it is 2. So having got the character of a reducible representation like this, it is possible to easily work out its irreducible components using the reduction formula. Let me write the reduction formula for a second time. Number of times ith irreducible representation occurs is 1 by h sigma chi I r gamma r n r. We know ammonia belongs to C3V group. The character table of C3V is written by the side. Only the character part alone is written C3V. Identity 2C3, 3 sigma V. This is A1, A2 and E. 1, 1, 1. A2 is 1, 1 minus 1. E is 2 minus 1, 0. Forget about area 3 and area 4 for the time being. So number of times A1 occurs, it is 1 by 6 into, this is A1, 1, 1, 1, this is gamma, it is already earlier written, it was 4, 1 and 2, and NR. NR is the number of operations in the class. E is just 1. Number of operations in this class is 2. Number of operations in the third class is 3. So you multiply and add this. 1 by 6, 1 into 4 into 1 plus 1 into 1 into 2 plus 1 into 2 into 3. This is 1 by 6 4 plus 2 plus 6. This is 1 by 6 into 12. There are 2 A1 errors as a factor of the original reducible representation. How many times A2 occurs? 1 by 6. Similarly, you do the multiplication. A2, it is 1, 1 minus 1. Gamma is 4, 1, 2, and NR is equal to 1, 2, 3. So multiply these numbers and add 1 by 6. 1 into 4 into 1, that is 4. 1 into 1 into 2, that is 2. 2 into 3 into minus 1, it is minus 6. So it is 0. And number of times E-type irreducible representation occurs is 1 by 6. E is equal to 2 minus 1, 0. Gamma is always the same, 4, 1, 2. And NR is 1, 2, 3. So multiply and add 4 into 2 into 4 into 1 plus minus 1 into 1 into 2 plus 0 into 2 into 3, which is equal to 8 minus 2 plus 0. 1 by 6 is there outside. So it is 1 by 6 into 6, 1. So we find that there is a factor E-type error belonging to the original reducible representation. So the original reducible representation is now consisting of 2A1 plus E. This is how the factorization is done using the formula. Yes, 2A1 plus E. We can explain this aspect further by one more example. Let this be the question. Write a reducible representation on the basis of pi-type p orbitals of S-cis butadiene and reduce it to the irreducible components. Suppose such a question comes. How will you work it out? It is cis butadiene about the carbon-carbon single bond. This is CH2 double bond CH, CH double bond CH2. About the single bond, the CH2 groups are on the same side. Double bonds are made up of overlap between p-type orbitals which are perpendicular to the plane of the molecule. So we shall write the sigma bonding skeleton in this manner, and the p-type p orbitals, pi-type p orbitals by a dumbbell, upper one plus, lower minus, plus minus, plus minus, plus minus. I name the p orbitals as p1, p2, p3 and p4. This belongs to C2V group. This is the principal axis, C2, and at the molecular plane B, XZ plane. XZ plane. this is the y coordinate or y axis. Molecular plane is xz plane. Now write reducible representation, identity 2C3, 3 sigma v. Identity keeps all the basis functions unshifted. So 1 plus 1 plus 1 plus 1, it is 4. Then C3, sorry, I made a mistake. It belongs to C2V group, not C3V. So I'll rub it off and write class-wise C2V operations, identity C2Z, sigma V X Z, sigma V dash Y Z. 1, 2, 3, 4. So under identity it is of course 4. C2Z, if you rotate it about the C2 axis, you can see P1 get exchanged with P4 and P2 get exchanged with P3. So every basis function gets shifted to new locations. Its contribution is 0. So 0 plus 0 plus 0 plus 0, it will be 0. What is sigma V X Z? The plane of the molecule. This is the molecular plane. X Z. All the p orbitals remain there, but because of reflection, the negative lobe comes to the top and the positive lobe comes to the bottom. So as if every orbital is multiplied by -1. So -1, -1, -1, -1, it becomes -4. Whereas sigma v y z, this is the y z plane, by reflection, the p orbitals get shifted from the left side to right side and the right side to left side. Because of complete shifting, their contribution to character is 0. It will be 0. Now use the reduction formula. Number of times A1 occurs is 1 by 4. In this case, you don't have to worry about NR because number of operations in each class is 1. Being an abelian group, every operation is a class by itself. So you just multiply the character of reducible representation with the character of irreducible representation denoted by the Mulliken's notation. So A1 is 1, 1, 1, 1. So I will write 4 into 1 plus 0 into 1 plus -4 into 1 plus 0 into 1. This becomes 1 by 4 into 4. This is 0 minus 4 or it is 0. There is no A1 irrep as a component. Na2, it will be 4, 0, minus 4, 0. This is gamma. A2 is 1, 1, minus 1, minus 1. So multiply and add 4 into 1 plus 0 into 1 plus minus 4 into minus 1 plus 0 into minus 1. Minus 4 into minus 1 is 4. So 4 plus 4 will be 8 and 8 by 4 it will be 2. So there are two A2 type irreps as factors of the original re-rep. Then B1, work out B1. This is the original reducible representation. 4, 0, minus 4, 0. This is B1. 1, minus 1, 1, minus 1. Multiply and add. 4 into 1 plus 0 into minus 1 plus minus 4 into 1 plus 0 into minus 1, or it is 4 plus 0 minus 4 plus 0. 1 by 4 is there outside. So it becomes 0 by 4 or equal to 0. There are no B1 type irreps. The number of times B2 occurs is 1 by 4 into 4, 0, minus 4, 0. B2 means 1, minus 1, minus 1, 0. And if you multiply and add 4 into 1 plus 0 into minus 1 plus minus 4 into minus 1 plus 0 into 0, 0 into 1, sorry, 0 into 1. So it is 4 plus 0 plus 4 plus 0 into 1 by 4 is there. So it becomes 2. So what is our conclusion? The original reducible representation is made up of 2a2 and 2b2. This is the factor result. 2a2 and 2b2. So the four-dimensional irreducible representation is made up of four one-dimensional irreducible representation, which are 2a2 and 2b2. All these are irrupts of the C2V group. Cis butadiene, 1,3-butadiene belongs to C2V group. In the next video, we shall work out many UGC net problems coming from this matrices, character table and the reduction formula, etc. Until then, bye-bye.